This system would allow the water to be pushed down off the pipe so they could have a dry place to work. The habitat was an 8-foot by 8-foot cube structure placed over the top part of the pipe. After air is blown inside to squeeze the water, the men could stand on the ledge to perform their work in a hyperthermic chamber. This allowed them to remove their diving gear and safely use tools to perform complex repairs and maneuvers. One of the tasks they had to complete was the removal of an inflatable plug in berth 6. This plug had been inserted almost 2 weeks before to protect the oil contents of the pipe and stop any hydrocarbons from escaping. This plug was an airtight barrier that held tightly against the pressure pushing down from the habitat chamber. A wrench was retrieved in order to loosen the valve on the plug. Kasim Ali passed the wrench up to the 4 men working around the pipe. Then he pulled himself up onto the ledge to remove his diving equipment. As soon as the valve was opened, a shocking force immediately overtook the group. Water rushed into the habitat and down into the pipe. This instant flush of water pulled the men and all of their equipment into a tornado of water swirling down the pipeline. It was so unexpected that they barely understood what was actually happening to them. In such an unlucky moment, they were extremely fortunate to settle from the water in a spot that had an air pocket for breathing. The GoPro video captured the men in the moments just before being sucked in, then everything went completely black. As you hear the rustling and movement, it's shocking to hear them start to talk. They were actually shouting at each other within this pipe that was supposed to be full of crude oil. The horrible irony is that this air that was allowing them to breathe was actually the cause of the swirling water tornado that brought them here. So how exactly did this happen? The inflatable plug that they were removing was supposed to be separating 1,200 barrels of oil from the air and ocean water around it. In that case, it would have been a matter of routine to remove the plug and proceed with their work plan. The air pressure in the habitat would have been pressing down on a heavy column of oil. The oil would have been settled level between the 2 pipe openings in berth 5 and 6. Nothing out of the ordinary. Unfortunately, they had no idea that there was a column of air under that plug, and a lot less oil in the length of the pipe. As soon as the plug was deflated, the high-pressure air from the habitat rushed down the pipe with such force, it pulled the men, their tool and screw tanks, into the pipeline. Because the habitat pressure was suddenly released, the ocean water violently pushed inside and swirled into the pipe with the men. In a wild swirl of air, ocean water and tools, 5 men fighting for breath. After what must have felt like an eternity, the swirling settled, and they found themselves in a pocket of air. Chris Boudreaux, the lone survivor, described the unthinkable moment of being sucked into an oil pipeline like this.
Tornado, everything just spinning and beating up and happened so fast. They couldn't react. After that, all I remember, I didn't even remember actually getting fully in the pipe. I just remember getting pulled through the pipe at unbelievable speed. I don't hold my breath no longer, but shoot, and you're holding your breath for too long. After a while, your body, your lungs just fight. Yeah, we explode, you see a noise. Your body suffering to pull air. Unbelievable night, man. Your eyes burning. Every time you try to open your eyes, you're pitch black, you can't see nothing. Your throat burning. Your ears ringing. Your body sore. And at that point, I tell myself I was gonna kill it.
Once they stopped, the men took a quick inventory of where they were, how they were feeling, and whether all 5 men had made it. They began shouting back and forth to find each other and confirm that they truly were inside the pipe together. It was just so unbelievable, but it was the awful reality. Trying to comprehend where they were in the pipeline was a lot harder than it seemed. They were completely disoriented and had no idea how far they'd moved down the pipe. This pipeline section was 1,200 feet long as 4 football fields. The pipe had undulations and weld seams or where supports were placed. These variations in elevation allowed air pockets to form. Once they got their bearings, it was clear that they were all battered, but alive. In all the disorientation, they weren't in agreement as to which direction would lead them back to berth 6. After some discussion, they decided to link together and shuffle as a group toward one of the ends. The The entire pipe was coated with thick, slippery oil sludge. It was exhausting to keep fighting against the oil and barely moving while dealing with broken bones, battered organs, oil in their eyes and nostrils, and all of this in complete darkness. At some point, after struggling for an hour, they encountered a shocking problem. The seawater level was rising. They were holding their heads above the water, but the first in line noticed that his face was now only 6 inches from the top of the pipe. There was no way to continue like this. Some of the men were seriously hurt and wouldn't be able to move much longer anyway. Chris Boudreaux and Kazim Ali were the first two leading the group. The other men, Yusuf, Faisal and Rishi, were the next three in the pipe. It was decided that Chris and Kazim would try to hold their breath and see if they could find another pocket of air. They promised the men that they would fight to get out and return with help for everyone. The two men held their faces high in the water for as long as possible, then held their breath to swim forward looking for air. Their struggle brought them to a second pocket of air, closer to the riser pipe that might lead them out. They were ecstatic to find two of their teammates resting in this section. It felt like this was all they needed to make their escape. They almost used both bottles of oxygen to move them to the next section, but Kazim's injuries were getting more serious, and he wasn't able to move quickly. Together, they decided that it would be best for Chris to take what was left of the oxygen and make a swim to the end of the pipe to get help. He placed the tank in front of his body and pushed it along as he squeezed forward in a narrow 2.5-foot tube. When he got to the riser end of the pipe, he was struck with a frightening thought. What if this was berth 5 and not berth 6? He would swim up nearly 60 feet and simply run into an inflated plug. There would be no air, and his tank was almost empty. He said a prayer and pushed off the bottom to make his way to the surface. After more than 2 hours in the pipe, Chris was relieved to find he had reached the top of the oily water at berth 6. He banged and screamed to try to get the attention of the rest of the ship team. One of the searchers finally found him and helped him climb out with a chain. Chris was overwhelmed and exhausted. He explained that there were air pockets in the line and that all the men were still alive. He was rushed to the hospital after letting rescuers know that there was air and that they were hurt, but alive. Up until this point, the other members of LMCS weren't sure that they could even be alive. They assumed that the pipe was full of oil, and the men would have drowned in minutes. They also knew that any oxygen tanks would last up to an hour each. It had been more than 2 hours since the men had been sucked into the pipeline, but finally, this was a glimmer of hope. Once Chris explained the situation, divers in the water tapped on the pipe in different locations and received a tapping response from inside. The trapped men must have felt overwhelming relief that someone knows that they are inside. They knew that professional divers and equipment of all kinds would be out on the ship above them. Oxygen tanks, rope, lights, help. Hour after hour they waited to see a glimmer of light or hear the metal clang of oxygen tanks coming down. But they saw nothing. They heard nothing. Not only were they suffering with their injuries sustained in the initial flush, they now struggled to breathe the acrid, oily air. Each hour increased the carbon dioxide content of this limited air supply, so breathing would become more and more challenging. And so they waited. No matter how the debacle of the non-rescue came about, it is a desperately sad reality that these men were just a few hundred feet from salvation. But no one ever came. They struggled in pain, knocked for attention, and attempted to move themselves to the exit. It must have been a crushing realization after days stuck in the oily pipe. No one was coming. The actions taken by LMCS, Pariah Fuel, their sister company Heritage, and the Coast Guard are much debated. It is claimed by some that Pariah prevented divers from entering the pipe to save the other men. Pariah claims that there was no viable plan to get the men out without risking more lives. Some believe that the men were certainly dead, and the banging was from something else. The Coast Guard, LMCS, and family members who were professional divers all have their own version of the events. The facts that cannot be denied are these. 4 men were alive at 5 o'clock on Friday when Chris Boudreaux was rescued. Many people agree that they heard banging on the pipes from inside for nearly 48 hours before it stopped. After the bodies had been recovered, 2 autopsies were performed. Though the autopsies did not agree on the time of death, it was clear that all the men lived until various times on Saturday, and some appear to have lived until Monday. We are not sure if the men succumbed to their injuries, or ran out of breathable air, or even drowned trying to swim to one of the pipe exits. A commission of inquiry was formed in Trinidad and Tobago. Their findings are scheduled to be released in August of 2023.
Because everything inside my poop and I rescue quicker. Everything inside you open and rescue is going on. Nobody was making us the best.
今個聖誕舒服福，一齊準備禮物俾朋友啦！加埋茶幾嘅禮物，正正贊用一按即通，40多間茶樓隨你配搭，將你嘅體貼心思表達成窩心心意。
Hello?
Hello, Chris. Hi, how are you?
Not bad.
Okay, good. Thanks. Sorry for the delay.
Yeah.
Was a bit much traffic on this Friday. Okay, so today we do 1 hour and 45 minutes. It's a bit a longer session today.
Oh,
Okay. That's news to you?
yeah, I didn't know.
Okay. Yeah. So according to the schedule, that should be, yep, because today and next week they would be both 1 hour 45, so 3 quarters, huh? Today and next week, so to basically have half an hour more. Is that okay for you still?
Yeah.
Okay, so then we do it until 8. Yeah, what do I say? Until 8 o'clock, 9 o'clock your time. So exactly, huh?
Yeah.
All right, then you take a break in between, huh? That's for sure. It will be quite intensive. Okay, so let me just share my screen with you. All right, here we go. And into here. So we go a bit back. Sorry, it's just a bit flashing by. So we continue with electricity.
Yeah.
And just a couple, we discussed quite a few things 2 weeks ago. Where we stopped was more or less basically here, the various ways to calculate power. And maybe just as a brief side remark, I mean, for A levels it's okay, but in say real life, just to make you aware, of course you will apply that. For example, this one is a very easy, very comprehensive one that you say, okay, because in your household you have 220 volts, right? Usually.
Yeah.
And then you will have a device which says maybe 1000 watts, for example. And then out of that, you can always easily calculate how many amperes you need in order to run that device, say vacuum cleaner, hairdryer, whatever. So if you take the tip, say this 1000, that make it easy by 1200, that's a 1200 power divided by 220 volts. So that's roughly about 5 amps. Huh? So you see that quite often in the household, you have 5 amp, 10 amp fuses as well. And that's quite straightforward because you are calculating it on 220 volt it's called then single phase DC, also the AC DC, that's alternative current, direct current. For 220 volts, we usually have AC, also alternative current. So when we do that calculation here, you can take the value as they are under normal household conditions, like we have them in Hong Kong, for example, or in Europe, in quite a few other places. But if you have, for example, direct current, like in the US, and you have a different voltage, then you cannot make the calculation simply as such. You may have to introduce some correction factors, huh? Just to make you aware. We will not deal with that in A levels. Or when you go to factory installations, or say a washing machine, a tumbler, then you usually have 380 volt. That's then so-called three-phase, because you will have a earthing, not just plus minus, but an earthing. And for that, you have apply more correction factors. You still use the base calculation, but there will be some correction factors introduced, and which means in reality, when you do the, let's make it here, if you do the, and you want to calculate the current, so you do your P over V, then typically the correction factor is underneath here, huh? And less than 1. So correction factor is usually less than 1. So that means it will become bigger, the current, so to speak. But that depends on the situation. But just to say, this is not the current, this is a correction factor or a coefficient. Huh? So sometimes life is a bit more difficult and complicated than what we calculate, but that's fine, at least as we have the basic understanding of how things work. Huh? But this is the very common one, so you can easily calculate basically the amps you need in order to run a certain device, because you're on a fixed voltage. I think that was the most important one to keep. Then I would like to go forward, sorry. Okay, so for this one, I would like to do some exercise here. Back. And we had that as question. More power. Okay, just a sec, sorry. I have a bit slow connection. All right. So one of the issues we discussed that about 2 weeks ago as well is the potential difference. And you may recall that we defined that the potential difference is basically the work being done for 1 unit charge. Do you remember that somehow, Chris?
Yeah.
Okay, somehow, right? So the one thing I would like to clarify once more is, well, not once more, but because there's the potential difference and there's the EMF, right? And they're both defined as work done per unit charge. And that one is exactly the same. So of course, it's always the question, what is then the difference between the potential difference and the EMF? And of course, they both are measured in volts, right? Because so, would you have any idea, excuse me, what the difference could be maybe between potential difference and EMF when we talk about a circuit like this? Because we may talk about the potential difference, maybe a battery of 12 volts. But I will correct myself in a minute. But do you have any idea what the PD and the EMF might actually define or deal with?
So potential difference, the energy that can be provided by the battery.
Okay, good. Yeah, you're on the right track. Just the other way around. Then it fits very well. So when you compare these two, and okay, let's say we build in a resistor here. Oops, sorry. So like that, and that should represent the resistor. Then which one would be the PD and which one would be the EMF?
I think the PD is the battery and the EMF is the resistor.
Oops. So when you have a potential meter, where would you apply that in order to measure the potential difference of the resistor?
Huh?
When you have to measure the potential, when we have here, so we have a resistor here, right?
Yeah.
Or let's make it even, we would even have two resistors actually. How would you measure the, well, or what do you measure across the resistor? Would you measure the EMF or the PD?
EMF?
The PD.
Oh.
That's fine, because it's just words. In that regards, I mean, and EMF is really an unfortunate term, but what you said is absolutely correct. Just flip the words, huh? To say one is about how much energy is provided, basically, also work over charge, which we call voltage. So in that sense, it's basically a bit like energy, we can say. And that's why we typically have here as well. Also, it's a bit a strange form. We usually have a simple E here, right, for the EMF. And that is a bit related to energy. So you can somehow make that mental link to say, okay, the EMF of 12 volts, oops, here is actually of what energy is provided, because it's work over charge per unit charge. Also the work, which is energy, is per unit charge. And of course, we know there's a unit charge floating here, or ultimately going on with the electrons. So they have to be moved, right? And that's where, of course, somehow the word electromagnetic force is coming. That we say, well, nothing moves without a force, right? From Newton. Of course, you may give some at the beginning, give it a nudge, but that still includes a force, and then it may move forever in vacuum, no gravitational fields, whatever. But there was somewhere, somehow, once a force involved, or it continues if there's another force resisting it. Otherwise, it would either stop or go even backwards against, together with the force which is stronger. In that regard, it's very simple. And as we are now talking about electricity, there's a lot of similarities with mechanical, but still. So we measure. Oops, that was supposed to be round. And here we measure the voltage, huh? So across. And why do we measure it across? Chris, would you know that? Why? Because, and I just make it here. And it doesn't matter if it's before or after. And here I measure the current with an ammeter. Huh? This is a voltmeter. So why do I put the ammeter directly into the current and the voltmeter across?
Because when the voltmeter is parallel with the resistor, then it receives the same voltage.
Good. Okay. Yeah, good one. Okay, and across is, of course, you need to have a potential difference, as it says, right? It's like our most obvious one when we talk about the gravitational field, and we have a height difference, delta H. So we have a different potential energy, as we know, if I compare this one to this one, right? So it's similar, but as there's a force going from, say, left to right, for example, in this example, because it's electricity, so it's not linked to any gravitational field, but still there's something similar going on. So I have to move it across the resistor, right? And that, of course, needs a certain, well, force, meaning times the distance. Ultimately, we have the electrons moving. So we have work being done per charge, right? So that is always a bit confusing. That just says per charge. And the charge is, of course, more than just one electron, as we can't really measure that, at least not in the days when that all was found out. And that's why it's per coulomb, right? Where we introduce the coulomb for the charge, and in that regards, it all fits together. So, okay, yes, so we have to measure across a difference, so to speak, and there will be a difference, and that's why we call it the potential difference in the resistor, because they have to really move against it. And here we just measure, well, the current, right, the flow. It's like a flow meter in a pipe when you measure how many liters per second, stuff like that. That's why it could be either here or here. It doesn't really matter. Just to say, of course, it has to be in the flow. There's no difference. And if there would be a difference from here to there, that would be very bad, which in reality may occur, but in our models, they don't. Huh? So that's important to remember. And the EMF is actually, like you said, the energy provided. Also, I mean, in plain English, which is not really applicable for physics, but it helps us to think about, that's where the energy is being provided or produced, and this is where the energy is being consumed. So at the end of the day, it has to fit. They have to be equal. That's a certain simplification, but that's how we calculate and can design circuits in an ideal world, in a model world. That we say whatever energy has been provided, of course, is the energy which is being consumed. Of course, we know it's transformed, and the energy here is just, well, one form of energy, in this case, like say electricity, and hopefully it all comes back here, so to speak. But as there's a resistor, usually the resistor will be as such that there's some heat going away here. So, but the energy, of course, is just transformed from electrical energy into heat energy. And if we look at the complete closed systems, of course, what has been gone into the system comes out of the system. Is that so clear?
I remember my teacher said that
Mm-hmm.
potential difference means the it's like difference between the potential energy of the electrical energy.
You may say so. You may say so. Yes.
But that means it's stored in the.
I know what you mean. Okay. Now, no, it's just because it's work, also energy per charge, right? So it's the energy you need to provide in order to move it across that resistor. So of course, if there would be no resistor, you would not have a potential difference. Then it's just simply like a pipe, whoop, goes round, a hose goes round. Of course, there's nothing being, well, as a resistance, so to speak. So henceforth, you would not even talk about it. The moment you have such a resistor included, that could be, of course, that could be a lamp, for example. We know that it will, the filament lamp, for example. So there has to be work provided or energy in order to for each unit charge in order to move the electrons, so to speak, because they're a physical part. So they have to go against whatever resistance. It could be like a counter pressure, or like you say, potential makes absolute sense, or it could be a pressure difference. If you think about a pipe, if you have no pressure difference, it will not flow. Imagine in space, on Earth, it's clear. That's why whatever, any vertical pipe, whatever goes down, goes easily down, but it's very difficult to pump it up. So there may be an analogy if you say, I have to pump up water here for my shower compared to here, and this is the water tank. So if I would have, that's why quite often the water tank is on the top. Then you have the advantage of the gravity that there's some natural pressure to go down here because it has a higher potential here, obviously, than here. So there's a potential difference in energy. It's actually very similar here, no big difference. Of course, it's electricity, but in terms of energy, there's a difference in energy, and you have to provide that. Sorry, I should say it here. The energy to go from here to here because you have to go against it. So it's like if you would be here, you have to pump up the water so that it reaches the shower here. And you can only do that if you have here a higher pressure than up here, which then means it moves up the water molecules. And that is a bit the same here. You need a higher pressure in order to move the electrons to the other side, because there's a bit of resistance. So of course, horizontal is a bit strange for us. We are so used to gravitational, we rather think vertical. But in electricity, it doesn't matter. That's the main difference, right? Whatever you have, it's really about in which way the current flows, and hence what the resistance is being there on the way. And in order to overcome the resistance, you need to have a certain energy, this one, to overcome it. Otherwise, it would be like if like a notch to a stone in space without gravity and all. Once you give it a notch, it just floats and floats, goes and goes and goes. That would be the same for the electron ultimately. If you give it one notch, it will go around, but because there's resistance in it, you need additional energy to overcome that. Same thing if you have that say paraglider in air, or a plane, of course, but just the paraglider is more obvious. Then, of course, it needs some additional force in order to move it against the wind blowing. That would be a similar like this one. Okay.
Yeah.
All right. Huh? Okay. That's. I mean, it will not be. It's good to understand it. Usually, there's not really a question about it, but it's good to have the basic understanding of what's really going on. So when we go into that question, this one.
Is the power?
Yeah, I'm just coming to it. My bad. Okay, so I made that just as a reminder. So that's why the question may be something like typically it may say, and quite often in the questions there's no difference between an EMF and a PD. That's not so good, frankly speaking. But you may be told that there's a battery with a PD of 230 volt. That's strictly speaking not really correct, but quite often some of the questions are like that. So don't be misled then. Huh? So actually, it should really see to be the EMF actually. So what we say here, so we have the rate at which energy is transferred is by a 230 volt main supply. So this one is now say avoiding that pitfall. It just says the main supply is 230 volts. So we would say that would be the EMF of the source. And it provides 8.0 amps, and we are using a heater. Huh? And now we want to know the calculate the rate of energy. So that is what would be the rate of energy in simple symbols, so to speak? What do we have to calculate actually? What would be the real word to be used here?
The EMF times the current.
Okay, okay, yeah, that's correct. But what is that? As another word, because you would usually not say the rate of energy. Nobody would really understand in everyday terms, right?
So because 230 volts of EMF means there is 230 joules of energy transferred per coulomb of charge.
Super, very good,
And
Chris. Yeah. Okay. Yep. So
also
actually, that's what it means, right? Yes, exactly. Okay. So yep. Sorry. So 230 joules per coulomb. Exactly. So that's what it means. So that's energy per charge, right? Perfect. And the rate of energy, what does that really mean? Or say, if you would have to say somebody, I don't understand, what is rate of energy? What would you tell him? What other word would you use?
The power or rate of energy transferred.
Yeah, power, yeah. It's power, right? And rate of energy means probably something like energy per second. Of course, it could be energy per hour or whatever. Typically, we do everything per second. So, yeah, rate means something time. Something if we take E for energy over time, right? Something like that. Okay, power, great. So, and now obviously when we talk about that, that's where already. So we say that, and you said, okay, I have to actually take the EMF, or let's take the voltage, that would be the times current. Huh? Goes back to that simple formula. Yeah. Okay, so that would be now, like you said, 230 times 8. So we will get something like 1840. And what unit of measurement is that then?
Watts.
Watts, exactly. Yeah, good. Right. So the rate of energy, the power, the energy per second, we measure that in watts. Huh? Exactly. And that would be on the other hand joules per second then. So here we go back to our traditional one. In normal circle, but we focus that on watt. Huh? Exactly. All right. Good. So in this one, we say there's a power station. That power station makes, of course, we probably have to deal with the mega and the kilo. 220 megawatt. That's neither big nor small. And it has an output of the voltage in which it provides that energy to the grid is at 200 kilovolts. Huh? And of course, we want to know what is the current supplied.
The power divided by the EMF, or
Yeah, okay, exactly right. So because this is supply, the power station supply, so rightfully so, you are to talk about EMF, and that's very specific and very good. And you will see that probably in many cases it just says even maybe PDF, but quite often it just avoids, just talks about delivered at 200 kilovolt, right? So then there's no question about EMF or PD, so to speak. Okay, yeah, absolutely. So you have the current is out. So it's just another rearrangement. So, and of course the calculations are very simple. It's more about to get it, because the numbers are quite realistic actually. So 20 megawatt would be how much to the power of 10?
10 to the power of 6.
Okay, and 200 kilowatts.
10 to the power of 3.
Okay, all right. So we have 20 divided by 200, and on the other hand, we have 10 to 6 to the 10 to the power of 3. So what would we get for that? Without calculator, for example.
Yeah. So I think first we simplify the
Yeah.
10. So the top one would be 10 to the power of 3, and the bottom one would just be cancelled out.
Close. You're on the right track. Just the numbers don't match yet. I mean, are not yet where they.
Yeah. And also the.
So when you say simplify.
Because also 20
Okay, I see what you mean. I got it. I know what you did. No, that's fine. It's correct. It's just, of course, you can do it in different ways. So obviously, I had it differently done in my head, but you're absolutely right. So absolutely. So you can simplify this one first, for example, correct? And then you go this. What you can do as well, for example, is to say, well, I take out this 0 and go here to 4. Take out that one as well. Because then it's the most simple of them all. Then it's 2 divided by 2, which is obviously 1, and I have 2 left, so I can as well go like this. Right? You saw what I did, right?
Yeah.
You just take that out and transfer that to 1 unit higher, and then of course it's just 10 to the power of 2. But of course I can just as well write 100, because when we deal in that dimension, then we rather don't say 1 times 10 to the power of 2 ampere. We rather say 100 ampere, of course, in this dimension. Let me just see. Yeah, maybe that one, number 8, because this is a very typical one, especially as it's getting colder and colder, hopefully one day. So we have a 330 volt supply, that's very normal. And we have an output power of 1 kilowatt. Huh? 1 kilowatt. So typically, of course, you would rather talk about the voltage and the ampere, but okay, it's a question. So we say we have an output power of 1 kilowatt. Now, what we want to know here is that we use that for a heater again, and we want to know what is the resistance of that heater. So this is related to the bathroom heater, for example, quite typical, which you can turn on, so you get some heat out of it. It says you get 1 kilowatt out of it, okay? In whatever way the heat really is coming to you, you leave that aside. Just basic. And so we have to calculate what is the resistance of the heater.
Find the current first and then use the volts and current to find the resistance.
Yes, can do it that way. So can you do that? Do you have everything you need for that calculation or not?
I think we do, because we can do like 1000 divided by 230.
Okay. And then you get what?
The current.
Okay.
And then we do the 230 divided by the current.
Okay, all right. So you say the power divided by the voltage gives you the current, huh? And then say that again, please.
The voltage over current.
Voltage over current. Huh? Exactly. Yeah, very good. So you see what this shows actually is that you do not necessarily have to remember the so-called 3 equations of power, right? Let me just go back quickly. These. So these are like ready-mades. So you could jump. It's a bit like a puzzle game that you say, okay, what do I know? And what do I need to know? And hence I have to rearrange. But you can, of course, always go with the basics. This is one basic, then the other one, of course, is this one, like you used it. And out of that, you can basically always calculate the remaining two, in most cases. So, or it's allowed, just to say, if you recall that you can, for example, do this one, or as a resistance times current square is equal to power, then of course you can just rearrange this one and get the current out of it, because we have the power and the other way around, of course, in order to get the resistance. Huh? Both is absolutely okay.
Yeah.
Just to say, so you would not need in all cases have to go all the way. If you know the shortcut is fine. Huh? We leave the numbers aside. It's just about the principle. Okay. Well, this is 17 is too. Now we've done that really. Same thing. So we've done that. This one is just the other way around, number 18, but that's just the same formula applied the other way around. So you see that there's not. I mean, you have formulas with 3 unknowns first of all, and then you have to rearrange it. So it's just a matter of what is given and what is being asked, and hence you have to rearrange accordingly. So let's leave that aside. Yeah, maybe the number 19. That's maybe not too bad. So we have a calculator with a 3-volt battery. EMF, strictly speaking. And we have the resistance of 20 kilo ohms. So that seems to be quite something in such a small calculator. And what is now the power? From the cell to the circuit of the calculator.
3 squared divided by 20,000.
Okay, then we get how much?
180,000.
And that's what measurement?
The ampere.
The power?
Well, oh, wait. It's the watts.
Okay, so when you look at it, does that make sense to you?
Because I want to make sense with the formula, because V I and then I equals V over R.
Okay, you can, let's see. I mean, 2 steps, it's fine, Chris. When you look at that, right, you have a tiny little battery of 3 volts. So this is really very small, right? But very typical for such an calculated, probably not even a scientific one. And you have 20 kilo ohm. So there's a really high resistance, but you see a bit the link between how that works between voltage and resistance. Of course, they are not asking for the amps, but they are, when you then think, wow, I would that little calculator would need 180,000 volts. That's like oof. Because when you think that a hairdryer needs about 1,000, what did I say, volts, watts, needs 1,000 watt. So 18, that's 180 vacuum cleaners. That's what such a calculator would need as a supply. That would probably not really work. Huh? And that's a calculator. Imagine if you talk about a notebook or one of the smartphones, etc. So they would need a gigawatt, for example, and that cannot be. That's why I'm asking, right? So you can just sometimes say, well, does that really make sense? I say, well, something somewhere did not match. So we can. So let's start again. It's fine. So you say, right, like this, huh?
Yeah.
Okay. So and you want to know what? Because you will go the same way again, right?
Yeah.
So how do we get the I? Maybe I miss. Did I miss something? What you told me, maybe, Chris?
V over R.
Yeah. Did maybe you said that and I missed it?
So is it the 20? So divided by 20,000?
Yeah. And I mean, because you said square, that's fine. But if you jump directly to the formula, I mean, to the one which is the result of what we are doing now, which is good. This is very nice. So we will come to the right result, not like this, but because you said 3 squared, right? So that means you obviously squared the voltage. And when you do that, also, I mean, in other words, when you jump directly to the second one, then you get V squared over R.
Yeah.
And you see that, right? You can, of course, now come from this angle here, that you say the I is V over R, hence you can say henceforth P is voltage times voltage over R, of course, is just V squared over R. So somehow, somewhere, you took that one, but you squared something. And then you got already into the watts. I mean, that's how I heard it.
Yeah.
So the approach you do is fine. Always, you can always go with these two. You can, as we said, you can basically solve always everything. Then you can just say, well, okay, what do I need to know now? Which one of the three, or which one of the two are given, and which one of the three I need to calculate. So okay, this time this one. So I need to calculate power. Power is one of the, let's say, basic formulas, if you want to say so. V times I, very helpful. Then you just combine it, and of course you get this one. Huh? So, or you can go straight to this one, because you can say, well, I need my V, I need my resistance, so I can just go straight to this one. This is always helpful if you can't remember or if it's not given in the formula book. Huh? All right, so the result would be actually 0.45 milliwatt, actually, even. So that makes about sense, because if you have, in other words, if you have a very small voltage but a very high resistance, you cannot get much power out of it. It's a bit like saying, hey, of course, if there's a really high resistance, there cannot be much flow coming out of it, right? Flow is nothing else but energy per second, kind of, in a certain way, or related to that. So if I have a really high counter pressure, there cannot be much energy coming out of it, especially with such a small power difference. PD, EMF in that case, excuse me, PD of 3 volts. So that is really not pushing much pressure into the system, into the circuit. And then the circuit on its own has a really huge resistance comparatively. So that means in the end, there cannot be much energy transported per second in that system. Huh? This is a bit linking it, right? If you would have a 300 volt calculator, that would be really dangerous. I would not really like to touch that one, frankly speaking. But even you see, when we work on the notebook, of course we can charge the notebook 220 volt, but you see there's always a transformer involved. Huh? You never plug in 220 volts directly into the notebook. Could be, in theory, it could be, no problem. You would just need an additional transformer inside the notebook, which of course we would not like, because it would add to the weight. That's why the transformer is in the so-called charger. But the charger is nothing else but a transformer, actually, which makes sure that the 220 volt get tuned down. Depends, 10, whatever the voltage is. I would not even remember right now. Maybe 5 volt, something like that is quite often. 3 volt even, like what we have here, actually. But then, of course, we plug it into the main supply, 220 volt, but it gets tuned down to 3 volt. But of course, there's still quite then some amps going through, so we still get sufficient energy supplied. Huh? So that's a bit the link between low pressure, high resistance can only result in low energy supply or usage or whatever pushed through. If we have very high voltage and very low resistance, then of course we sure get a lot of power out of it. That would be ideal, right? If you have high pressure and the low resistance, of course you would expect then the water, so to speak, is just flowing through the system, more or less related to the higher the pressure here, the EMF, then of course, or the difference, which makes the system work in force, in energy, in potential, the more goes through it. Huh? Is that okay?
Yeah.
Okay. All right. I think then this is related to time. That means we go a bit back insofar as we take the power, but look into the time of how much or how long was energy being used or supplied. And this is a bit an application of this one, that we can say, okay, this is a big challenge for the electric vehicles, of course, right? Because you have to carry the energy with you, hence the battery. You are not producing on board the energy you need. You store it, that's the battery. or you would have to have a really long cable, which is obviously not working anyway. So, okay, so I have to carry the energy with me. So it's one of the big questions then, how much energy can the battery store? And therefore, how far in that context can I drive? This is a bit, so the car battery, of course, 12 volt is not what we have in EVs. This is just maybe to provide additional, say, aircon when it stands still, try rid of the audio, something like that. So that would never drive an EV vehicle, actually. Is it just a standard car battery actually to start the combustion engine, so to speak, and to provide the energy to move all the masses in the combustion engine that it can start to operate as what it is, a thermal engine, or a device based upon thermal energy provides power output. Okay, so now when we go back and say we have a 12-volt battery, that would be the EMF again, of course, and we can supply 10 amps. That's not too bad. And we can do that for 5 hours. So, of course, nobody would ask how many joules of energy the battery transfers. Under normal circumstances, everybody would be very happy to say, well, 10 amps is really nice. As we know, household fuses are between 5 and 10 amps quite often. So that seems to give you enough power to drive vacuum cleaner and so on. And now we want to know how many joules. So how do we attack that question?
So find the power.
Okay.
It's 12 times 10, so 120 watts.
And what else do we have to include into the whole calculation now?
If we want to find the total energy, then use the time.
Okay. Okay, yep.
It should be 5 times 60 times 60.
Exactly, yeah. Okay, 60 times 60, or 5 times 3,600, exactly. All right, okay, so there's a 120 times 3,600, so that's something like, okay, that's a lot. So I get that number. Joule, would you agree with me, Chris? Oh, and I should, of course, ask you what unit of measurement.
Wait. Is it 2.16
Okay.
megajoules.
Okay. All right. Very good. Exactly. So joules, and you already simplified with the 6 digits to 2.16. Yeah. That just made it here complete. First, we say the power is the usual what we now always see, the I times V. On the other hand, we know that energy is nothing else but power times time, or in other words, if power is energy over time unit, of course, we can just go the other way around. Multiplied with the time, simply because, well, power is energy per time, like we did it. Okay. Okay, I think that's good enough. Did we discuss number 2 already, Chris? No. I mean, it's part of what we discussed, but no, I think no, we didn't. I just had somehow oops, deja vu, as it's so nicely called. So now there it goes exactly. Well, it goes a bit to the difference between EMF and PD, but it's a bit, of course, typical multiple choice. Huh?
C.
C, yeah, okay, good. And why do you say C, Chris?
Because it has to be 1 unit charge. The
Okay,
energy transfer per 1 unit charge driven around the complete circuit because it's
yeah, very good.
cell.
Okay, exactly. Yep, right. So this one makes, sometimes you make a question where there is then even this one, the source is then certainly the consumer of energy, something like that. So here it at least is always source, 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 source. Okay, transferred. So until here, it's all the same. And then and transferred, of course, is rather transformed. Huh? But you don't want to be too picky. Because ultimately the energy is transformed, right? You even when we quite often talk about transfer, it's ultimately transformed. And very important, of course, quite some may be tempted to say through the resistor. Um, yes and no, but not really correct. Ultimately, not 100% correct. So this is the only one which says it. And here, of course, the unit charge is missing very clearly. And of course, this one is wrong anyway, so to speak. Yeah. So it plays a bit with the words, of course. Huh? And that goes back to complete circuit. It means we really have to look at it and say, okay, it's what has been transformed. So it's the source, but it has to be what has been transformed. So that's why EMF and PD have to equalize each other. Okay. Um, Maybe take number 5. So we have a lightning strike, average current, and it lasts for 2000. What would be that symbol, Chris? Would you remember that?
Micro.
Okay. So, right. So, exactly. Quite often people make the milli, but it's one more. Exactly. Okay. Good. Milli and micro. All right. So, the charge. So, what is the basic? I mean, here it's more about, of course, the units of measurement. I mean, the dimensioning, the powers. Um, how do we have to calculate the charge?
The current times time.
No, exactly. So it's a bit like what we had before, where we say power is energy, also the other way around. Excuse me. And we said energy is power times time, right? Or delta T or T. Typically, you rather talk about delta T. It's a bit more elegant, but of course, T is just fine. Huh? So very similar. Here we talk about the charge, and here we talk about the energy. All right. So that means what is I? What is the current?
10 to the power 3.
Okay. And what is the time?
2000 times 10 to the power negative 6.
All right. Okay. Okay. And henceforth we get how much?
60 coulomb.
Okay. Yeah, very good. 60 huh? So and when you look at it, that's why the powers are always nice, right? So basically we have 3 times 2. Again, like before, we have 3 times 2 makes 6, and then we just have to go with the other zeros. Then we end up on 60. Okay. Yeah. Good. I mean, I don't want to go to that further. Then obviously it just compensates each other that we have 20 left, 3 times 20 left. That makes 60 because the rest is just equalized in the powers. Huh? Okay. Okay, let's go to number 10.
Um,
Let me think. I think something's wrong here.
Yeah.
Yep, that's the wrong. Oh, that's right. Okay. Oh, just a sec. We talk about this one. Oops. That's question number 10. Oh, okay. Let's put it. And let's see. I think that would be this one. Yep. Yeah. All right. So, what is the? That's a very difficult question.
The direction of the conventional current is from left to right in the
Yep.
electrolyte.
Okay. Yep. So just go from left to right, huh? So, yeah. I mean, sorry to throw it very days, but that's better. Okay. So conventional, huh? And why do you come up with that, Chris?
Because the copper ion is receiving the electron, so the conventional current is in the opposite direction.
Okay, all right, okay, that's an interesting answer actually. Good. And if you look at the this one, what could you draw from that?
It's
Or,
the negative is on the right.
yeah, exactly. Okay, no, I mean I like your answer more because it's more about chemistry, physics, so to speak. This one is just like remembering of how the circuits are drawn for the plus and minus poles. Huh? Yeah, okay, good. And of course, what is the direction of the electrons flow in the connecting wire? Well, there's not much difference to the if it's the wire or the electrolyte, but in which direction do the electrons flow?
Clockwise.
Clockwise, exactly. So go like that. All right, exactly. Just as long as so we could as well make it here, but that would not be so interesting because yeah. But so obviously something has to flow, right? Or two parts have to flow. Exactly. All right. Then question B. So what is the total charge? So what? It's nearly more of a chemistry question than a physics, but it's somewhere in the gray zone in between.
Because through the electrolyte, so because each chloride is giving one electron, and then on the opposite side the same thing is happening, so it's only 3.6 times 10 to the power 16 electrons.
Okay. Yep, that's a good point. That's a good thought through. And now this is what is that number telling you? That what you just said and I wrote down. What is that?
Number of electrons in
Okay.
8 minutes.
Yes, also within that time period, right? I mean, because it's within 8 minutes, we have to sometimes to be really careful of what they write. Sometimes they say this is we let it run for 8 minutes, and then the 3.6 times 10 to the power 16 pass within a minute, but they may not write it like that, like this. Sorry, per second or per minute, or I don't know what. Depends a bit. But they may just write it actually and say within a minute, and suddenly somebody only sees 3 times 6 and 8 minutes, whereas you are right, this is what has flown already within the time period of 8 minutes. Huh? And we don't want to know the flow rate or whatever. We just want to know the total charge. So what is missing still in our, what do we have to add? Let's put it like that. That's better said. What do we have to add in our calculation?
I think
I mean, you said it right. Huh? So we have these ions. So we have electrons, like you rightfully said. So
I think divided by the number of electrons per coulomb.
Okay, I see. No, it's actually very straightforward ultimately. When you think, so you have 3.6 whatever 10 to the power of 16 billion gazillion, right? But that just tells you how many are. But if you want to know what is each one carrying, because that's what it's all about in the end, right?
So
Is
I
each
think,
one,
is
yeah?
it 1.625 times 10 to the power negative 19?
Yeah, very good. Exactly. That's what it's about, right? We say, okay, I have one tiny little p unit, or one unit actually, which is very, very tiny, and it carries exactly that charge, 1.665 times 10 to the power of minus 19, right? And what would be the unit of measurement for this one?
Just coulomb.
No. If you were to,
This one
yeah,
is.
yeah, you're right. I mean, it's coulomb per electron to be very, very precise, right?
Yeah.
When you then multiply it with the number of electrons, then of course, or the one per electron. The other way around, of course. Sorry, my bad. Then, of course, it multiplies itself out. But typically, we just say this is the charge per electron, so we just write it down like that quite often. Yep, exactly. So, of course, one electron doesn't really move the world, but a big number, yeah, that moves quite something. And what is now the charge if we calculate it?
3.6 times 1.65 times 10 to the power negative 3.
Okay. So, what was the number you got, Chris? Say it again, please. The first one.
I calculated 5.94.
Okay, yeah. Okay, exactly. So it's still tiny, right? It's still minus. Also, minus in the terms of 10 to the power of minus, I mean. So it's obviously not 1 coulomb. It's still a 1,000th of a coulomb. So that's probably not so much, actually. But it always depends on what is the relative sizing we are talking about, right? When you're going on to atomic level, then yeah, that's something very different compared to what we need in a power supply or at home. Okay, what would be then the current in the circuit?
The charge is divided by 8 times 60.
Okay. By delta t, right? So hence worth, okay, 8, so 5.8 times, 5.94 times 10 to the power minus 3. And we just say, what you said, 8 divided by 60, huh? 8 over 60, exactly. Okay, and what would that give us?
Wait, why is it was it times 8?
Aha, sorry, sorry, that was meant to be like that, excuse me.
Oh.
Yeah.
But then is it So divide by 8 times 60.
So okay, I mean to make it better actually should be. So the idea is just to say divided by 8 over 60, right? Also, so divided by 8 times 60. Why do I say, excuse me, my bad. Of course. So, sorry. Like that. Because we had this 1 to the second. Yeah.
So 1.24 times 10 to the power of negative 5.
Okay.
Or wait.
Let me see. Yeah, yes, you are correct. So what would be it's correct, Chris. What would maybe be a bit easier if you thinking this well, like kilowatt, but of course we go the other way around. So how could we express that a bit differently? Maybe more easy when we talk.
12.4 microampere.
Yeah, very good. So, of course, when we talk about circuits, electronics, then we rather talk about such kind of currents, right? That's absolutely for sure. So it's really, again, that's why the world of energy grid and is a very different world with especially high voltage and all compared to the world of electronics, right? So somebody designing circuits thinks in very different terms compared to the one who does a whole complete electricity grid, or maybe the one designing factories, houses, and so on. Huh? That is crystal clear. All right. Okay. So this one is well, used to be something which was important. Of course, it's still in experiments, but it's a long time ago, Chris. But what could you think could be a very practical application of what we have in front of us here before we go into the questions? This electron tube. Of course, we need that in experiments. That was the early days of how physics experiments were conducted before we had larger machines like these electron colliders. But in practical applications, could you think of something which would have become everyday usage based upon that principle somehow? It's really a long time ago. So, I mean, yeah. So, I mean, TV screens were based upon that principle. Huh? Also, really the old huge, because of course the principle was still a bit differently because it was a beam which was shooting electrons, and but that's why it was called a cathode ray tube, a CRT. That's how the TV shows, TV monitors worked. That's why they were huge beasts before LED came up and all. Huh? So that just to mention that it's a very different world these days with with the electronic circuits actually, compared to where it all started from. When you really have these massive devices, can you imagine this one? A tube, a vacuum tube made of glass, evacuated near close to a perfect vacuum, then have the electrons moving from wherever to wherever as part of a circuit. So that was and if you wanted to have that in large scale, you needed the respective, amps and everything else. So let's calculate that a bit of what happens in such a situation.
4.5 times 10 to the power of negative 3.
Okay, yep.
Times 3 times 60.
Okay, so in other words, we go back, even if it looks very complicated, that's why I chose to still do it. In the end, it's not that complicated, right? It may look complicated. There's a diagram, but at the core, it goes to the same question. This is more like something the scientists had to build in order to make the experiment, for example, and to see what's going on, or to identify and say what is moving here really, identifying ultimately electrons, stuff like that. Huh? But in its core, it's straight to the point here. Okay. Now, the number of electrons that hit the anode in 3 minutes. So, how do we do that?
Charge times, I think is 6 times 10 to the power of 18.
Okay, so you want to know the number of electrons, huh? Okay, yeah. So let's call that n. That's always a good idea to have that as n. And so you say the charge.
Yeah.
Okay, so we just calculated it at 0.81, or well, now we can really go far and say 8.1 times 10 to the power of -1. That's a bit extreme. You may do it, but you don't have to, just to indicate. It could be done like that as well. Why? It makes calculations a bit easier. What is the value you have to do the charge per electron? Or you have the total charge, right? So with what do you divide that total charge?
Number of electrons per charge.
Okay, but you want to know the number of electrons, right?
Oh,
yeah.
Then it's the charge per each electron.
Yeah, exactly right. So charge per electron, exactly. So it's a charge per electron, something like that. And what would be that value again?
1.6 times 10 to the power of -19.
Exactly. And you see why then quite often we do it like that, because 8 divided by 1.6 roughly is easy, right? That's like 5. Then we just have to go here and then we just come up with the right answer, right? So we can then as well say in the first attempt it's around 5 times 10 to the power of -18, for example. So we have an easy answer, but of course that's especially helpful when you, for whatever reason, would not be allowed to use the calculator, right? Then you always try to make that as simple as possible. Then you just have to deal with the powers, and the rest is, well, it's really easy to calculate. Okay, and now we go into the potential difference between the cathode and the anode. So there you see, right, now we rightfully talk about the potential difference between these two. And you can see as well, because in a vacuum, what would the in tendency not have in these
Air,
two?
no air in between.
Yeah, exactly right. So they can really, what we have provided here as the electromagnetic force, which is then obviously going into this difference between the two, which is then obviously being used to move these, that is very explicit, electrons from one place to another. There we really see the very nice practical, not practical necessary, application or of what we discuss in all these circuits with PD, EMF, and so on. So that is a nice illustration in so far. So hence now we have the potential difference, 75 volts. So now it's a nice question. What is the energy gained by the electron as it travels from the cathode to the anode? So when you go back to what is the potential difference in abstract, in theory, in abstract terms, so to speak, or as a formula?
The difference in like energy. So,
yeah. Okay. over what?
Over charge.
And which specific charge? Can I just write this one? Because you rightfully said difference in energy. I like that. So what do you have to add underneath as well? What I've not done yet?
The difference in charge.
No, the difference, right? If we say one, we have to say the other, so to speak, right? That, of course, later on goes into math when you talk about differentiation and so on. Then the whole thing fits together even more so. So as we say, it's basically the work provided per unit charge, or the difference in work per charge difference, so to speak. Okay. Or we can as well, of course, write what, like, oh, you, but it's not that precise, huh? But it's not wrong. Okay. So what does that mean now, and what do we want to know?
To know the energy per electron.
Do we? When you look at question C?
The energy gained for one electron.
Okay. So what is there for our interest when we look at the three elements or parameters? Which one do we want to know from the three? So calculate the energy gained. Which one of the three? Say again, sorry?
The work done.
Yeah, exactly. Yeah, work done equals or energy gained, energy lost depends on the directional flow, for example. Exactly. All right. So it's mathematically, of course, it's mega simple. That's obvious. But it's about the basic understanding of what we are doing, right? So we talk about potential difference times the charge, right? And all on the level of one electron. So we have to be a bit careful in that context that it's not suddenly taking the whole charge, because we had that. So we want to know, like we had it here, right? Total charge. So these questions always have to be a bit careful. Do we talk about now of the total charge, which they provided already, most likely? Or is it another charge I still have to calculate again? Or is it maybe, in this case, like per electron? So what do I have therefore to calculate, Chris, if I want to know the energy per electron, actually? So it helps sometimes just to add such kind of an indices, right? An index. Then you know, I'm talking about just the energy per electron or for one electron.
So it's just the charge of one electron.
Okay. And times what?
So 75 times the 1.6.
Yeah, exactly. Yeah?
Times 10 to the power negative 19.
Right. Exactly. So you can see on the other hand, right? I mean, it's obvious, but of course the potential difference, with which we say 75 volts. So sometimes, again, as I say, it helps to think of the pressure difference, so that we are not too. So it helps clearly to move them from one place to another. Without that, they would not move. If the potential difference would be zero, they would not move. Of course, something will go wrong here. That's for sure. And how this and the apparatus, we don't have to understand what is really going on here. There's obviously something else involved which we do not know yet, but we'll learn to know. And in that regard, because in that regards, then yes, we have then the same field. That's why sometimes there's a potential field. So there we go back to gravity, and this then the link you can make the potential difference, then it can be further adjusted, and then you will have something like a gravitational field here between these two poles, or the cathode and the anode in that case. The moment you have a mass in it, like the electron, but you need, of course, to have a charged one, otherwise you do not go from one place to the other. Or, of course, you could do the same with the proton, you just flow the other way around. if it's coming into that field, then whoosh, it gets moved. Huh? It's the same thing when we talk about our gravitational field. It's a gravitational field. The moment it has a mass, it's the same thing. It's per unit charge, and the gravitational field is out per mass, per delta M actually. The moment you have a mass in the field, you get the force. Huh? So there's a very high similarity for quite obvious reasons, because they try to align that as well as far as possible. Okay. So, and we get, just to make that finish, we get 1.2 times 10 to the power of minus 17 joules. So that's really tiny, but of course we talk about 1 electron. Huh? Okay?
Yeah.
Okay, all right. So, I mean, you see the questions here are not so complicated. It's more about keeping having it, you have it very clear. It's very good to see. And just then be in such cases like such an apparatus, just be clear, okay, it's an electron involved, many electrons involved per electron, charge within a certain time flown, or the other way around, that you have to take then what is one charge, the number of charge, like here what we did. Huh? How many charges have been involved in that time? Okay, we I think we have come to the end of that one. And I would just like to start, nevertheless, with the Kirchhoff. But before we do that, Chris, maybe take 1 or 2 minutes of break, and then because it's a new chapter and it's something else. Huh? Is that okay?
Yeah.
All right. So let's just continue in about a minute. Huh? Okay. Huh? So, Mr. Kirchhoff, is it okay, Chris, to continue? Yeah. Okay. I mean, he's very important. Some of the laws are very basic, actually. You would think, okay, nice to have something like that named after myself. But it always is a matter of sometimes who figures out what at what time. Huh? And this is very important. So he really dug into it. Most of it is quite obvious, but the application is tremendous, because without that, maybe somebody else would have found it out at a later stage, most likely, is really the core of all the electronic circuits, or any circuit. It doesn't have to be electronic. Electronic is just what we do nowadays. Long time ago, have you ever seen maybe a movie or so about the origins of computer science or something like that?
No.
So there's the whole, just a very 1-2 minute is that when in the Second World War, one of the key issues was to encrypt messages so that the enemy could not know what orders were given by the other army side. Huh? Seems very obvious, but they became more and more sophisticated. The Germans became very good at that. maybe you've ever heard about the name Enigma, otherwise, which is nothing else but Latin, and it means a riddle, basically. An enigma is a riddle, but it's a Latin name. So they named the machine Enigma. It was, of course, at that time mechanical. So you had very different views, and you have to offset. When, like, the oldest encryption and most obvious encryption in the world is when you say, "Oops, I have A, B, C, D, E," and I go the other way around. So that means I replace A with Z, B with X, C with X, with Y and X. So of course, if I write all, it will be very different, but it's very obvious that it's very simple. But that's how it started, right? So you have one view where you have all the letters here, and then you have another view, and then you position them relatively. So that means you start to replace one letter with another, you make it a bit more complicated, you introduce a third view, etc. So that was a bit the background. So now, of course, to decipher that, let's say the British, to figure out what the Germans were up to, that involved a lot of many mathematicians, actually. And at some point, they started to automate that, not just manual work. There were people who were good at crosswords, stuff like that, who were involved in that base somewhere in the UK to decipher all these messages. That was sometimes very vital, obviously, to know a bit in advance, but you could not let the enemy know that you have found out the key, right? And when you think of today now, we send so many messages around, or we do banking on our phones, somewhere, in the middle of other people, maybe, but send the signal out. So if you intercept that signal, you could very easily read all the information about that person, right? The bank account number, the password, but so it has to be encrypted. Same story, just nearly 100 years later. And what used to be for the army and the military, of course, is now used by us everyday people, so to speak. So the principle of all that has not really changed. Just, of course, it became more sophisticated. The means have become different. And instead of having very complicated, huge machines, we can have that in the palm of our hand, in our smartphones, for example. And the reason I go back, these machines were really huge, and they were all very physical. Also, they didn't have circuits, also electronic circuits, but they had all the wires in it. So you really had to have a wire, a cable, like you have usually nowadays to plug in maybe a TV to a computer or a player. These were all the wires you had to by hand plug in. So they looked like huge stations where you had all the various cables, and you had to change the setting of the cable in order to get a different circuit. Just to give a bit of background. But that was all. The principles are all the same. It's still Mr. Kirchhoff, which applies. And what he said was to say, well, what is coming in goes out. Seems very logical, right? So that what is the current into a point must be equal to the one going out. Of course, that's under certain ideal situations, but still. Or you can say, well, if I have one current, it must be the sum of the two others, which come into a point. Makes a lot of sense as well. So, or if I visualize that, it's like if I have a point P here, go like that. So, same thing, right? So that current one must be equal to the current afterwards. Or if I have such a split point, now I just say, okay, I goes in, so I1 goes in, and it goes out. Of course, I could turn it around and say, well, if 2 and 3 are coming in, then of course they must be equal to the one going out. Same thing. It's very logical, right? No, but that was. But if you think what we have in the computer these days, there's those integrated circuits, these ICs. They're not just millions, billions of those. But everything the computer does in the end is nothing else but all you have these circuits. Then it's still the same old story. Either you have current or you have no current. Still that. There's nothing more behind. So that's why you may sometimes wonder if artificial intelligence really deserves the word. Some claim that humans are not much different. I don't know, just to say. So this one was in the olden days, is there current? Also no current, of course. no current there, and there is current. So either the current goes through or there's no current going through. And based upon the Boolean logic, that's 0-1 logic or binary logic, you can build up highly complex circuits which are able to, what we see nowadays, our own programs, well, or what we call artificial intelligence, to surf the net, gather information, rearrange it, and answer questions, write essays, guide a missile, stuff like that. But the principles have not really changed. They're all still based upon that. But of course, in highly sophisticated ways. Now, luckily, we don't have to become too sophisticated at that level. But nevertheless, some of the questions become already a bit tricky, even on what we are dealing with. So, of course, just making a very simple example, right? Following Kirchhoff's law, say, okay, if I have something like this, and I have something like that, so what therefore has to be the current in that missing one?
4.5.
4.5, right? And again, exactly. Very, very obvious, but important. And let me see. So, of course, when we talk about integrated circuits, it becomes a bit more complicated. And the following, let me just see, it goes like that. We have it like this, and we have it like that. Okay, so now, so the simple question is, does it follow Kirchhoff's law, that circuit I have here? So what I
Yes.
have to check? Okay.
Because if the current going towards the center is equal to the current going away from the center, then it should be obeying the law.
Okay, as from the first one, or in other words, first law from Kirchhoff is the sum, right? So the direction seems to be okay, right? So in, out, out, so they are not hurting each other, so to speak. That's fine. Now, does it add up? That will be in the right way.
Yeah, it does.
Does. So when you have, what would you say, what do you compare, for example? What goes into the junction, right?
Yeah.
So what is the sum of all those going into the junction?
3 plus 2.5 plus 1.
Okay, how much?
6.5.
Okay, and what about out?
So 4 plus 2 plus 0.5 is also 6.5.
Exactly. Okay, yeah, very good, exactly. So, right, it seems at first glance, of course, not so complicated, but still. So just follow the basic principles. And the formal statement, just to write down nevertheless, is his first law, also Kirchhoff's first, is the sum of all in is the sum of all out. You know? Just as we applied it. That's his so-called first law, according to him. Sum of in is equal to sum of out. Okay. Then we have a second law, actually. Let me just see. Like this, like that. We go here. And we put in two resistors. So, two resistors. I make it a bit sloppy. And goes in here. So R1, R2, EMF. So that is actually what we already discussed a bit before. So like what he said, what must be the same all across that circuit now?
The current.
Okay, yep, current is all the same, huh? So, and on the other hand, what can we say about the EMF? So if that is true, in and out,
R1 plus R2 equals the EMF.
close, you couldn't say R. What would you have?
The potential difference of R1 and R2.
Yes. Okay, yeah, very good. So, okay, so let's write it like that, huh? PD of R1 plus PD of R2, or in other words, we could say as well the VI. Huh? Is that correct? Ah, yeah. Wrong, sorry, my bad. IR, now I. So, with what we have is IR plus IR2, huh? Yeah. So that means EMF, and that is a bit now a more practical writing of what we discussed before. So the EMF must be of the battery must be equal to the sum of all the PDs, huh? Across the resistors. So I could write it now from I whatever to. So the sum of all the PDs, or I could make it as well the PDI, huh? Sum of all PDs. So I have 1, 2, 2 in that case. The sum of all the potential differences across the resistors are the same. This is the second law. Huh? So which means, in other words, what is provided as energy has to be in the end fit has to be equal. It cannot disappear. It's actually nothing else but the same as we say for energy, right? More from the mechanical side, for example, that they have to balance, for example. So they always transform and be the sum of it, or they are equal then. Okay, so this is his second law. So that would be, okay, so second. What we can say to that as well is that, of course, when you go into the loop, so quite often it's mentioned as a loop. Well, no, not like this. So it goes around like that, huh? Yep, would be nice. It's more okay. So that's the loop. So when you go along the loop, obviously, then you have exactly that being fulfilled. So with this loop going around in the circuits completely, like you answered before, then you have that being applied. Okay, so let's do a simple example. I can just take that one here. So you have 10 ohms here, you have 30 ohms here. So that should be 30, sorry. 30 ohms. Of course, you have the current going around. And we have the situation now, which is a bit, of course, that's part of the question. We have two EMFs, which is a bit unusual. And then in between here, and we go again here, and sorry, here, just to make life a bit more miserable. And of course, we say here we have minus minus, and we have therefore plus as well. I just have to make sure I make the drawing correct. So we go here. Yep, nearly have to make it like that. We go here. Yep, okay. That's just make that a bit more clear. Okay. So here we have one with 6 volt, and we have another one with 2 volt. Huh? And of course the loop is like that.
Okay. Then because the 2 volt is opposite direction, so it should be 4 in total.
Okay, very good. Okay, so sum of EMFs. So first of all, sum of the EMFs is 6 minus 2 because of the direction. That makes 4. So here we see it's a bit unusual, but here we talk about like kind of vectorial, right? Because the direction starts to come into play, hence the plus and the minus. Okay.
Yeah.
And what is now the sum of the PDs?
Should be also 4.
Should be and what would that? How would he? But can we calculate? Yes, you're right. But how can we now go forward?
Current times 10 ohm plus current times 30.
Okay.
Yeah.
Okay, very good, exactly. And because you know how important that is, right? Because we say, hey, the current is in both places the same, so of course we'd have twice this one. If that would not be the case, it is, but just to say, then of course we would something like, okay, now what? How can I calculate that? And what do I can say? What can I say? Therefore, when I just finish the equation here or the calculation, what do I get, Chris? This is a bit more math than physics, but on the other hand, physics as well.
40i.
Exactly. So it's a very interesting point. Actually, you add up the resistor as well. 10 plus 40. Of course, you have to still multiply it with the I, and as it's in a serial, of course, you just multiply the same I, but actually, you just add up the resistors. That's something we deal with next time in more explicit terms, but you see it already here. Actually, that's what we do. We just add up the resistance. And then what can we say as a next step or the last step? Or what is now Kirchhoff's law? And henceforth the answer. When we look at these two.
The EMF supplied is always equals to the PD of energy transferred.
Yeah, exactly. Very good. So sum of EMF equals sum of the PDs, and henceforth, of course, 4 volt has to be 40I. 40 current or amp. We can already say amps actually, but it's better to keep the short sign, and then we'll only at the very end go to the. So henceforth, what is the current?
Uh, 0.1.
All right. So, here we go. All right. So it's again calculation-wise, that is usually all very simple. I don't know mathematically, but the laws behind are straight somehow. You have to understood them. That's great. And then you just have to apply them and know what they are talking about, right? So instantly that we have this is the core of the question actually, to realize the obviously one they flow in opposites, otherwise it wouldn't work. And hence we have 4 volts and not as an EMF. Huh? But that's an interesting question when you think about it. That you so what you can see here as well is a bit like whatever volt I have, as the net. Of course, in a simpler question, it would already been given the 4 volt, but it was dealing a bit with how do we get to the total EMF, so to speak. But you could as well say our famous car battery of 12 volts is given. So we have 12 volts, and I have resistance in the system or whatever, either 1, 2, 3 or whatever. So I just add up these resistors, but of course I have to multiply it with the current in order to get my voltage, right? Or the PDF, to be very precise. So hence it's comparatively easy to give some considerations of the dimensioning, that you can say, well, the 12 volt and the sum of the resistors, of course, is then influencing the current I get, so to speak. Now it's a matter of what you want to dimension, right? So if you want to have a very specific current for whatever reason, then obviously, apart from now, let's say car battery is always 12 volts or 24, you would not really vary that and say, I want to have a car battery with 18 volt or whatever. But you could then modify the resistors, right? Either you put in one resistor which is exactly giving the value you want, or for whatever reason you may put one or two or three in series, which gives you then the total resistance, and that will then define how many amps you get out of the circuit. Huh? In other words, with a given voltage, you can then influence of how many amps you get out by designing your resistors. And the resistors are, you can buy them in any electronic hardware shop. There are these spidery things, so only one left and one right, like this. And then they have these indicators that you know what resistance they really have. Then you can combine them. That's actually the start of a complete circuit in the end, huh? Of how you can make it. Okay, so that was a bit the start of what we're going to do next time. So we go into serial and parallel circuits and calculate then together with Kirchhoff's law what is ever then asked of us, what is the resistance in a certain sub-circuit, or what is the total current in a circuit made up of 2 parallel circuits and stuff like that. Huh?
Mm-hmm.
All right. Okay, Chris?
Yeah.
All right, okay. Well, then see you next Friday, and have a good week until then. Huh?
Yeah, you too.
Thanks. Bye.
Traumatized by the previous incident. Alright, man.